Okay, so let us start. This is basically almost a repetition of what we discussed yesterday in another section. So, but like you cannot take bath in the same river twice, so you cannot give the same lecture twice. So every time you try to repeat the same thing, it changes some way. So I think it will be little bit different. But essentially, I plan to say the same thing. So whether I say the same thing or not is a different issue. So just a quick check. Am I audible and visible to everyone?
Yes, sir.
Okay. So the first experiment for our control lab is control valve. So this experiment is regarding control valve. And yesterday I asked another question, which is I got good response. So what is the difference between doing an experiment hands-on and doing an experiment online like this? So we are doing some experimental lab. So what do you feel is the difference? What extra would you gain if we would give you the opportunity to operate those machines yourself? What is the crux? What is the difference?
The difference in accuracy of observation.
Well, yes, so that's what people said yesterday. Accuracy of observation. Any other idea? Any other thoughts?
Operating the actual instruments.
Operating the actual instrument. I'm getting fragments of what I feel, so I'll tell you, of course. Let me hear from some more of you.
If we do an online experiment, we tend to forget it as compared to the hands-on. We tend to remember it for long.
Okay, very good. What else? I'm getting very interesting points. Some more?
So, like while making the reports, we try to accommodate the points like precautions and sources of error. So those are the points which we sit and think for now. But when we go and do it in lab, it is something what we experience.
Okay, yeah. So all of those are excellent points. And if I am to add to this, my observation is that when you try to do something yourself, 100 things can go wrong, which you don't know until you are really trying to do something. So when you are trying to operate a control valve yourself, you will find that many things can go wrong. You're expecting something to occur, nothing happens. So that kind of things occur. So I think the true value of conducting these experiments is to have that feeling that so many things can go wrong, which theory never tells you. Theory always tells you that 2 plus 2 will give you 4. But when you are trying to put 2 and 2 together in an experiment, it's not always accuracy. It's not that you are getting 1.99999. No, you may, after adding 2 and 2, you may get 22. So that kinds of thing happen in experiments, and then you find, oh, it should have been 4, and then you see that, oh, these things I haven't done, and then you learn many new things. So that is what the experiments are for. And for this lab this year, since these things is dragging on and on, so I thought what I'll do is that I'll do a live session. So I made some arrangements, but this week-long lockdown has put that plan out of its track. We'll put it back, but today we'll will not be able to do that live session. Today we'll discuss a little bit of theory and other, what's the experimental setup and other things. And Monday, hopefully things will open. I told the same thing to other group also. Hope I am not lying to both the groups. And Monday I will go and take a video of that experiment. I take one of the TAs with me and we'll do the experiments, take a video, and then take some real data that day itself. And then give you the raw data and the manual. And I'll let you analyze the data. So in that case, you can imagine yourself as the standing observer, which in a group of 4, 3 people are like that. So you don't really miss too much if in that way. So if you are the 4th person who is actually doing the experiment, of course you miss a lot, but we cannot help in that. So I will do those experiments Monday, second half, hopefully. Now, so what experiment? What's the control valve experiments? I will of course tell you more about that. Before that, let me hear from you and see how much you remember. So tell me, what are the different components of a control valve? If you don't remember, you can pull your notes, something, and also look at it, and then also can tell me. So this is not an exam, so well, you can tell me by looking at that also. Palak Agiwal. Palak Agiwal. Jyotiraditya Aryan.
Yes, sir.
What are the different components of a control valve?
Control valve. I actually don't remember it. Like, can I see from the notes, sir?
Yeah. Go ahead, see
Okay.
and tell me.
I need to find that.
Okay. Anyone who remembers?
Sir, actuator was one of the components.
Okay. Valve actuator. What is that?
The part which moves in order to obstruct or let the flow pass.
So I think like it was the part which was which understands what the valve has to do.
So that receives the pneumatic signal. Valve top receives the pneumatic signal, and according to signal, it moves the stem. So there is a diaphragm which moves the stem. The stem is connected to the valve body. Valve body has a valve plug and valve seat. Valve body is a normal globe valve. So that is what a control valve is and looks like. So let me share my screen. So this is the same team which we were using the previous semester. So all the videos of control valves are here itself. So you, before plunging into the analysis experiment manual, you look at those videos again. So control valve, everything related to control valve that we discussed, and something more, as I told, will tell you today. So those needs to be brushed up before we do this virtual experiment. So a control valve, what a control valve does? Muskan Jain. Deepjoy Boshak. Awish Akhtar. सारे absent. Awish Akhtar. हाँ. Awish बताओ. Tell me. What control valve does? Control valve controls, of course. What else will it do? How it controls?
Controls the flux
Sir,
of.
it is used to control the varying the size of the fluid passage. It will
So
control
control valve controls the flow of the manipulated variable by changing the restriction. The valve seat is like this and valve plug is like this. It just goes up and down and changes the opening size. So that's how it changes the flow rate. So that's what control valve does. Okay. So what are the different types of valve characteristics? First, what is valve characteristics? Yesterday I got better response, I think. You see yesterday's recording, you'll see that I was getting very stronger response yesterday. You guys are a lot more silent. What is valve characteristics?
The relation between flow rate and the valve opening.
Okay, a little bit more technical terms.
It's the depth of the plug, and it's the relation between the depth of the plug and the flow rate. So basically, it could be linear, it could be higher sensitivity or lower sensitivity.
So it's a fractional lift versus fraction of maximum flow. Fraction of max flow versus fraction lift. So that is the valve characteristics. Now, so this experiment that I will be doing on your behalf is to obtain the valve characteristic curve. Suppose a valve is given to you and you cannot open the valve. Even if you open the valve, you may not know what's the characteristic of the valve. So we need to know what is the valve characteristics. So for that, we'll measure the fraction of maximum flow and fraction of maximum lift. And these two will plot, and then we know that what is the characteristic of that particular valve. We'll be given 3 valves, and the question that is asked is that which valve is which. Valve number 1 is what kind of valve, valve number 2 is what kind of valve, and valve number 3 is what kind of valve. This is the basic question we are trying to answer using the this experimental setup. I'll show you that. Achal Kumar, question. Okay, so that is the experiment we were trying to do. What is valve coefficient? CV. And what is the utility of this valve coefficient CV?
It's a specification of the valve, and it relates the flow rate with the pneumatic pressures.
Not pneumatic pressure, the high pressure drop across the valve.
Pressure drop, yes, sorry.
So it gives the flow rate for a given pressure drop. So there is a relation, flow rate Q equals to CV times del P over specific gravity, square root of. Look at that relation and they will find that CV is related to the valve size. For the same pressure drop, a larger valve will give you larger flow rate. So that is valve sizing. So that is called this valve coefficient. So this experiment has three parts. One is the obtain CV of that valve. Second, determine the valve characteristic for the three valves. And there is something called inherent characteristics and installed characteristics. So what I taught you in this instrumentation course is inherent characteristics. It's the percent lift versus percent flow for a constant pressure drop. The entire curve is obtained for a constant pressure drop. But when the valve is installed in the line, so it doesn't have any mechanism to maintain a constant pressure drop. So all it knows is that its stem is going up, flow is increasing, stem is going down, flow is decreasing. And when this happens, the pressure drop across the valve doesn't remain the same, it changes. So under those conditions, the characteristics is called installed characteristics. And this is not inherent because that depends on the pressure drop across the valve, depends on many factors, including the other line losses. So flow rate, this is pressure drop is a function of total flow rate. So that's why it's called installed characteristics. So these three things we will do. First, we will obtain the valve coefficient. We will obtain the inherent characteristics of the valve. Third, we will obtain installed characteristics of the valve. I will share you the manual from where you will know more details about that experimental details. But now I'll show you the setup. So this is the setup. So these are the three valves. And this particular thing that you are seeing here, let me make it a little bigger. It's not very clear because the picture is not clear. But I took it from the website of the manufacturer who supplied us the setup. So this is called Apex Innovations. And this is called valve positioner. So valve positioner is an instrument which make the valve stem travel by a certain distance. So this is required for a system where the fluid that is flowing through the valve is very dirty. So that gives friction to the valve stem, so that a small change in valve top pressure will not move the valve stem accurately. So the valve positioner takes the signal from from the pneumatic signal and then move the stem accordingly without relying on the diaphragm. So that's what the positioner is. With little more details are available in the manual. But first, let us see the flue arrangement. First, these are three valves are there. So we will not tell you, and I also do not know which valve is which. Apparently, this is linear, this is equal percentage valve, and this is quick opening valve. And these are also different arrangements are here. So you see, this is pressure is coming on the top. So this is pressure to close valve. So if the pressure is higher here, this valve closes. And this is pressure to open valve. So if you have pressure here, so this push the diaphragm here and pressure to open. So this is fail close and this is fail open. And this is possibly this here is a pressure trap. So this is also failed close. So it's pressure to open. So to open, you need pressure. So these are the three valves. And this is the valve stem which moves up and down. And this is the valve. This is the pipeline which is discharging to a tub. And this is the inlet line, just bend and comes here and push the water in this tub. This is the valve body. This is the actuator. This is the valve stem. And it's hard to see here. There is a scale which tells you what fraction of the fraction of lift. As the stem travels up and down, a small needle moves up and down here. From here, you will know that you can read that what fraction lift the current position is. And there is a rotameter which tells you what is the flow rate across the valve. And another thing it's not possible for you to see in this picture is a water column which measures the pressure drop across the valve in terms of column inches of or centimeters of water. So it's a very simple thing. It takes a pressure trap from here and simply makes a column of water here. If there is a here the pressure is atmospheric, so just whatever height of water you see here, that is that much pressure is across the valve. So that is the pressure, and the signal that comes here, there are two regulators, air regulators, from which you just move the knob, you'll be able to control the top pressure. So that's how you move the stem up and down and change the percentage lift. And this pressure gauge reads the supply pressure. There is a compressor here not shown. This compressor gives the supply. So these blue lines are all pneumatic lines. So blue plastic tubing, those are pneumatic lines. And this reads the supply pressure. What is the typical supply pressure? Not typical, most of the time. What is the supply pressure?
20 psi.
Yeah, 20 psi gauge is the typical supply pressure. And what is the range of signal pressure?
3 to 15.
3 to 15 psi. So this pressure gauge reads the supply pressure. There is a compressor which maintains 20 psi. So you'll always see 20 psi. So this is a vent valve. If you open it completely, it will drop. If you close it completely, it may go slightly above 20. So we just open it slightly so that the supply pressure maintained at 20 psi. So a small bleed is allowed from here. We maintain a 20 psi. This is a pressure gauge, a dial. It will show you 20 psi. And these two knobs you can change and then change the pressure here. These are the gauges which will read the valve top pressure. I'm not sure now. I'll go and see the setup, but I'm sure one of those reads, but exactly which one I am not sure at this point. You can also read that valve top pressure ranging from 3 to 15 psi. So if it's 3 psi, pressure is too low, so the diaphragm is pulled all through upward, valve is completely open. So if it's 15 psi, it's completely closed. But normally the control valves are not meant for complete closure or complete opening. Complete opening is fine, but complete close, there are some small leakages, or leakage always happens to the control valve. So that is what the setup shows. So while measuring installed characteristics, you will have to maintain the same pressure drop across the valve for all lift and all flow rates. So when you change the stem position, your pressure will increase. So you have to again control the flow rate to make the same del P across the valve. That's how you'll get installed characteristics. And if you don't bother about this pressure change, you get the inherent characteristic when you keep pressure drop same, and install characteristic when you don't worry about the line pressure drop. Line pressure drop, whatever it is, it is. And CV also I told you what it is, and this is basically the flow diagram of this valve. So the valve, so this is a tank in which these valves discharge, and there is a pump which put it back to a overhead tank. The back of this panel, there is an overhead tank. So the overhead tank feeds to those valves. So whatever discharge happens from here, that goes to the overhead tank by pumping through this line. I think this is the line which put it back to the top of this the overhead tank here. And overhead tank has an overflow line, because you cannot always maintain the same flow rate. The valves are going up and down. So there is an overhead, that's the overflow line. This is the overflow line. This is the overflow line, which maintains a constant head of water in the overhead tank. So that's all about the setup. That's all about the setup. Here is the diagram. I think this is good. Yeah. So this is the overhead tank I was talking about. This is the overflow line. This one is the overflow line. This is the line which feed to the valves. This through a rotameter. It comes to valve. This is common header, and it goes to valve 1, valve 2, valve 3, depending on which gate valve you remain open. And then it discharges to this one. And from here, there is a pump not shown. It goes and pumps here. And then this valve top pressure, there is one air supply, 20 psi supply pressure. That's the pressure gauge you have seen. Then this air regulator and this vent valve I was talking about. And I think this, since this is coming after the air regulator, it's possibly showing the valve top pressure. And there was one which before that, which will give you the supply pressure. So, or maybe there is nothing to measure supply pressure. So just you measure the valve top pressure, signal pressure. All right, so that's how we will be doing. So this is the del P across the valve, total del P across the valve. That is not exactly constant. So we have some measurement of pressure drop across the valve also. So this is dependent on flow. The total pressure drop in this line is dependent on flow. So this del P is constant because this is the head and this is the head. But because the loss is different depending on the flow, so the inlet pressure is different for different flow rates. So that's why you get the installed characteristics when you run without making this pressure drop across the a constant. Okay. So in a nutshell, this is what the primer required for you to understand and go for these experiments. Analyze the data. Of course, experiment you will see in me doing in a video. And some points may be hazy, especially in the install characteristic and inherent characteristic. Just read it from some textbook. I think our Stephanopoulos or any other textbook you can read and get a clearer idea about that. This is one of the simplest experiment we have in the control lab. So next week our experiment is a little bit complicated, pressure control trainer. So we'll have a little more discussion on those. Okay, so I think that's what I plan to discuss with you. If you have any question, let us discuss.
Sir. Sir, when we see the valve capacity equation, we have a pressure difference term. So that pressure difference term, does it include the pressure difference across the valve?
That is the del P across the valve.
And it does not include the pressure difference from above the valve?
No, that is pressure drop across the valve, and that's a design parameter. So when you select a valve, say suppose you have a line, you have some control requirement, you want to select a valve, you know the flow rate. All you know the flow rate. So which valve to select? So you have to specify. So this is the del P I want, and then you get the CV and select the valve. So that is the pressure drop across the valve, not the entire pressure drop.
Okay, sir. Thank you, sir.
Sir, are all the valves gate valves or is there a globe valve too?
See, these valves, just let me, my screen is shared, right?
Yes.
See, these are gate valves. Okay, these may be gate, globe, doesn't matter. These valves are meant to be completely open or completely closed. So these are not control valves. 1, 2, 3, these are meant to be completely open or completely closed. They may be gate, may be globe, doesn't matter to us. These valves by design, control valves, many of them may be gate valve, maybe globe valve, also doesn't matter. But for time being, let us consider most of these cases I have seen those as globe valves with an actuator mounted on top of a globe valve.
Okay, sir.
See, any valve can be made control valve by putting an actuator on top of it. It need not to be globe valve, need not to be gate valve. But many a time for chemical process, what I have seen, those are globe valves. Okay, so as per our policy, if you have any question, feel free to ask. If you don't have any question, feel free to leave. And I'll be here for another 10 minutes. So in 10 minutes, you can think of question, you feel free to ask. Discuss something, not entirely related to this control valve. Some question in mind, you can ask me, I can try to answer. Except when everything will be normal. That question I cannot answer.
Thank you, sir.
Thank you, sir.
You are very welcome.